So the next session relates to the new paradigms in science and technology. It will be moderated by Professor John Wood, who is actually the chair of the Attract Project Advisory Committee. John is the former Secretary General of the Association of Commonwealth Universities. And before taking this post, he was Dean of Engineering at Nottingham, and then Principal of Engineering, and then Senior International Advisor at Imperial College London. Without any further ado, John, the floor is yours.
Well, thank you very much, Roman. And it's a delight to be with you today, wherever you are around the world. I, for my sins, are in the deep countryside near Cambridge. Welcome to this session too. We've got three contributors today. First, Professor Tony Hay, who is currently Chief Data Scientist at the Science and Technology Facilities Council in near Oxford. And then we've also got Professor Barbara Pernici from the Politecnico di Milano, and finally Professor Tuuli Tovanon from Helsinki University. I'm not going to say too much about them because you can read their CVs on the speaker information. But I first got to know Tony about 20 years ago when he was the pioneer for e-science in the UK. And then he went off to be Vice President of Research at Microsoft Research before returning to the UK after he left that post. Tony's going to give us a short introductory talk, and then we're open to questions, which will come to me. So please use the Slido link, as Roman has mentioned. And Tony's talk is going to be called The New Paradigms in Science and Technology. Thank you, Tony.
Great, thank you very much for the introduction, John. Yes, I'm trying to convince you that we are at a very exciting nexus point in science and technology where a number of developments are coming together. So I'll quickly go through what I think are the most exciting developments and how we can take advantage of them to do more science, but also to do more innovation in business. So first of all, as John described, I did e-science, which I would describe now as data-intensive science, and my colleague Jim Gray at Microsoft called this the fourth paradigm. The fact that you did experimental science, then we did theoretical science, and in the 50s, when we had digital computers, we had computational science, where you needed to know about programming and algorithms and so on. But now we have scientists producing huge amounts of data. It's big scientific data. So it's not just big data, it's really gigantic data sets for scientists to try and analyze and get science out of this. And I would characterize what e-science is a set of tools and technologies to help you do data analysis, data mining, data exploration. So that's, if you like, the first breakthrough that really a lot of experimental science now has huge data sets, and how we analyze them and how we find small signals in those is particularly critical. So that's one development, that science is now big. A lot of science now has huge data sets. The second development is in AI, in fact, in machine learning. It's called the deep learning revolution, and it was spawned by this project called ImageNet. As you can see, there were a lot of images there, and they were annotated to say this was a dog, this was a cat, this was a house, this was a car. So they were labeled images. And what they discovered was that going from a particular type of machine learning based on neural networks, instead of just one hidden layer in the middle, if you had a large number of hidden layers in the middle, you really could do remarkable things. And what you can see on the next slide is the sort of images. So, not just a bird, but different types of birds, different types of cats, and so on. And how does humans classify, and how do humans manage to do that? How do your computer visualization tools, how do they do? And as you can see, in 2010, they were doing much worse than the human level of around 5% errors. They were up over 25%. But in 2012, there was a dramatic drop of about 10%, and that was caused by what's called deep learning, these neural networks with more than one hidden layer. And now in 2015, 2016, we now, with networks with over 100 hidden layers, we can get down to below human error rates. So in this area, which is a very exciting area for images, you can do better than human error rate by using these deep neural networks. And so not only in images, but also in speech recognition and other areas, there's been a large number of applications in industry of deep learning which have transformed your life, and we're using it every day without necessarily knowing that it's based on these deep neural networks. So you now have big data in science, big scientific data, and you have these possibilities of using AI and machine learning technologies to try and get science out. And this is where I work at the Rutherford Appleton Lab, and there's a number of facilities there. The Diamond Light Source is an X-ray synchrotron. The ISIS neutron source is where John was the director of this laboratory. Produces neutron beams. There's also a laser facility and an electron microscope, and all these facilities actually produce very large data sets, so large you can't take them back on a USB stick. You have actually to find some way of managing a terabyte of data. When you get to your university, the user can't put it on their laptop. It's becoming a real issue at how they manage and manipulate these data. And so what we've been doing at Rutherford Lab and labs like Rutherford Lab, like ESRF at Grenoble and so on, we've been applying what we call scientific machine learning to these data sets to try and help get new results. And just to show you that it's not just this lab, it's many labs. I'll give some examples from the US. This is the reason the beams haven't got any more tense, although there are plans to upgrade the beams of these big facilities. But what's really caused the deluge of data is the detectors have changed and dramatically increasing performance. So the doubling time is much faster, for example, than the Moore's law doubling time. So the experimentalists now get huge amounts of data, and finding significant signals in that data is now a major problem. So just to give you something, this is from a lab like the Rutherford Lab. This is Argonne. This is the sort of scope that they're looking at applying machine learning to a whole range of problems. So you can see here that there's astronomy and there's particle physics, of course, but there's also material science, there's biological science and climate models. So they're applying machine learning to try and get science out of a whole range of data. And this is just one of the US labs. There's also Berkeley and Oak Ridge and other labs also looking in applying AI technologies, these breakthrough technologies, to try and get new science. And so we're really at the cusp of exciting things happening in that space. And just to illustrate that, Google have a subsidiary in the UK called DeepMind, and they have actually used deep learning along with protein folding simulations to produce what is the best prediction of protein folding. It's called AlphaFold, and it is a tool used as machine learning and simulation to actually do the best predictions, better than anybody else's systems, for predicting protein folding. So this is an example of machine learning producing a really breakthrough tool in science. So machine learning and AI applied scientific data. Where are we in computing? Well, actually, we're at the end of Moore's law. What do I mean by that? Well, Moore's law means many things to many people, but basically it's the reason why your computers have got faster and cheaper over the last 30, 40 years. And it's because the processors got smaller and faster, and you could have more of them on the chip, and so it became cheaper. But as you can see from this graph from Intel, around 2010, the clock speed is the speed of the chip. You can't make it faster, the power, you can't put more power in, and therefore the speed up is decreasing. Although the number of transistors, you can still make them smaller, you can get more transistors on the chip, but you can't power them and make them faster. So the traditional Moore's law, just waiting a couple of years, your machine gets faster and more memory, that's ended, and we have now to use interesting, exciting times for doing computing after Moore's law. What are computer engineers going to do? Well, this is I talked about AlphaFold from DeepMind. This is their program that really did make a huge difference. Instead of the chess program, Go is a much more complicated game between two players. It involves a 19 by 19 board and many potential moves. And what DeepMind did was they trained their system by playing against itself, and after about 40 days, it became the best Go player in the world, able to beat the best Go player. And why that's interesting is because that's a different scale of computing. So at the bottom, you see a line from perceptron up to RNN for speech and so on, which is the sort of Moore's law line. And you see in the modern era, after the deep learning revolution, you now have a different speed because you're now using things like graphical processing units to actually go and do the machine learning for you. And AlphaGo 0 at the top of this involves a huge amount of computing. It's a different scale of computing. And actually, because of that, because of the end of Moore's law, that's unleashed a huge amount of creativity in chip design. So people are now designing specialized chips to do transaction processing, to do AI, to do neural processing. And this is just one example. There's over 100 different startups doing these new different types of chips. And this is Cerebras. And this particular chip is the size of a wafer. It's a 1.2 trillion transistors, and it's 100 to 1,000 times faster than the fastest GPUs that we can have today. So there's a lot of innovation because of the end of Moore's law, and it's a very exciting time because instead of just making things smaller and faster, you now have to think and do interesting things. And so you'll see a whole lot of different types of innovation coming from the silicon design industry. Okay, so end of Moore's law, applying AI breakthrough to scientific data. What's happening in general? Well, this is a statement from a colleague of mine at Microsoft called Peter Lampson. He was one of the pioneers of the early PCs. And he classified computing as three sort of phases. For the 1950 to 1980, we were figuring out, what computers can do, and things like the spreadsheet and simulations is for doing calculations. But in 1980, things like the ARPANET came along. We began to connect them up and communicate with computers, and that led eventually, yes, to the World Wide Web and also to social networks. And so that's what we've been doing for the last 30 years, from 1980, 2010 or so. And since then, we're now trying to get computers to really engage on our behalf with the physical world in a non-trivial way. So simulation, communication, and where we are now is trying to get computers to actually work with us to do intelligent things. And it's a very exciting time in computer science. So you all know about autonomous vehicles, smart cars, if you like, where you have sensors and can tell whether it's pedestrian with a car. It's still a long way, in my view, before you get large numbers of self-driving cars on the road. But in certain aspects, you will see these things without a doubt. And you're already beginning to see computer-assisted driving, but not wholly autonomous just yet. That's one example. And then you have now the Internet of Things, where you'll see AI involved in all of these areas, in the home, in healthcare, in industrial, in transportation, infrastructure. All of these things will become intelligent, if you like. And even your devices on your wrist or whatever. So this is an iWatch, and this is Skype. You can talk into Skype in English, and it'll translate it into Japanese so that my Japanese colleague hears me speaking in Japanese, and vice versa. So these things are transformed by actually your device here is transformed to become a supercomputer, because this can actually do the calculations in the cloud. And so when you do a translation, actually the translation's done the calculation in the cloud, and it comes back to your device here. So all these devices will be getting intelligent, and that's inevitably going to affect us all. All right. So where do we go from here? So we have the big scientific data, the big data, and actually using the AI revolution on the data. The AI revolution is going to affect everything. And so we can actually, in principle, apply that in industry or whatever. But in terms of science, Jim Gray and I and others cared about the possibility of open science, trying to make science more efficient, instead of actually having a laborious thing where you have data and literature and they're disconnected. You have to connect them together and you can combine them. And also you can use AI tools to find things in the data and the papers and put them all together. So there really is a transformation in the way we read literature, and there'll be transformation in the way we do labs. There'll be automatic laboratories which are using AI and helping you devise what experiments you should do next. So there really is a coming transformation in science. And it's because of the convergence of the big data in science with AI technologies and the end of Moore's law, with the innovation in chips. It's a very exciting time. And in the next 10 years, I think you will see a totally transformation in much of science, that we can do science in a much more efficient and better way. So John, over to you.
Well, thank you very much, Tony. And there should be a round of applause, but we can't hear it at this stage. Every time I hear Tony speak, I'm always worried about how I'm going to cope with this future environment. But we're now going to turn to our two other panelists. First of all, to Barbara Pernici from the Politecnico di Milano, where she is Professor of Computing Engineering. And Tony, you talked about the whole issue of very large data sets and the ability to extract anything meaningful from it. And I think that's nowhere more important in not just the tech side, but also in the wider social context. And perhaps, Barbara, you might want to give your thoughts about how that can be tackled.
Thank you, John, and welcome. Hello to everybody. I would like to answer your question, but just giving some examples, because of course there are a variety of possibilities that are open. And as Tony was saying, the computers have become able to do many things which were not possible in the past because of the technology, but also because of the way we were using them. But they are basically good in doing two things, which are computing faster and faster and storing information. And of course, evaluating similarities. So all the machine learning technology which is being developing will help us. On the other hand, there are many issues that are still open. And in particular, one issue is how to use this technology for different purposes, in particular for social and other applications involving also people. So we have been seeing basically the two uses. One is to do a lot of computations. The other one is to allow people to interact with each other. But one of the directions which is important is how to use the current technology and develop new technology and new ways of working, which are putting the two things together, which is not only interacting with physical things, but also to benefit from what are the functionalities. And I would like to give a couple of examples from some projects that I've been working on recently, European projects. One is going on, which is Crowd for SDG. From the title, you can gather that we want to put together crowdsourcing, so the ability of people to provide information to solve some problem. And our target are sustainable development goals. So in particular, we are focusing on climate actions. So what we are doing is to try to open challenges. And one challenge is open now. The theme is urban water resilience, where we are trying to involve communities to use also new technologies and recent technologies to extract information from the very large amount of data that is available. For instance, we have been doing this in this project and also in a previous project, which is E2MC, to analyze emergencies and to try to extract from social media important information, which is in particular the fact that you lack in the very first phases after natural disaster information from the ground. You don't really know what has occurred, like for instance after an earthquake or after a major flood, and you need evidence from the ground to know what to do and to provide information to first responders in order to be able to reach the place and provide the needed assistance. What you can do is to get this information, to try to get this information from social media, for instance. So in social media, for instance, in Twitter, which is publicly available, people are posting tweets and telling about things going on. And you can try to extract from those some information about current events. But it is a little bit like looking for a needle in a haystack. There are many tweets, millions of tweets, and you're looking for possibly very few images which are relevant to the event. Because you are trying to figure out what has been happening in an area which has been hit, and so people, of course, have many problems, and it is difficult to find information. But there is some information. Sometimes this can be very valuable for the people who are going to be there and try to reach the place and don't know where to go exactly. So in this context, you can help the crowd to, you can get help from the crowd to try first to select images from posts automatically, but then asking the crowd if there is some important information that should be used and can be processed further. So there you need the human judgment. And the mixture of the two things gets very powerful. And this is what we are working on and also for the future. Of course, the crowd can also help us to ask new questions, not only if some images is useful, but also other questions about the possibilities of intervention and so on. And so this is opening the challenge to follow up.
Thank you very much, Barbara. Well, you opened up the whole area of bringing the citizens in and ownership by the citizens, but also analysis by the citizens. We live in a world which is very fragile, on an earth which is going to be more fragile. And I'm going to turn to Tuuli Toivonen now, who is Professor of Geoinformatics at Helsinki University, perhaps to respond to how she sees those interactions occurring. Tuuli, you're muted.
Yes. Thank you very much for all of your thoughts and for the possibility to be here. I'm so excited about the developments what Tony was presented from my own research perspective as well, and for the whole world, of course, somehow how we could be using these big data sources, social media, but also teleoperator data, mobile phone data all together, or mobile big data all together, and artificial intelligence to be understanding what is happening at the moment as the world is facing so many crises. The COVID, of course, being one of the most evident one at the moment, and being geographical in a way. So most of the measures to fight COVID have been geographical, and the disease spread is geographical. So we need to be understanding the geographies of the world all of a sudden globally. And I think that that has made the wider sort of societal community to understand the challenges at the moment, which have been very well known somehow by the researchers already. So we also have been using social media data, as Barbara, for conservation research, but also for urban, sustainable urban research. And somehow what is so evident that in order to fight these big global challenges, we need to have information about people. And we need to be having information about mobilities, the spatial patterns of people, how people use space, how do they think, how these things evolve. And big data sources allow us to analyze these things. But of course, what we see is that unlike most environmental data, which Europe has been super good at creating infrastructures and programs for, actually this data, which is related to people, we actually don't have very good access to. So most of the individual level data that we as citizens produce, it's user-generated data after all. So almost all of that is owned by private companies. And even if we have access to Twitter, it's actually only 1% of the Twitter feed, and it needs to be collected all the time. So there is no central bank of Twitter that we could be analyzing. That didn't. U.S. Congress tried to do, the Congress Library tried to do that earlier, but it didn't succeed. So we don't actually have the resource, this information actually available for us researchers. And I think that is one of the fundamental challenges that we need to be sort of tackling in Europe at the moment, that how do we actually get information not only about environment in very detailed manner, but also about people. Of course, then we accept the fact that we are surveilled and tracked all the time. But if that, or as that is being done in any case by international companies, so at least to have that information to be used for research and also for social decision making is something that I would like to urge Europe to make sure that that happens. And I think that that relates also to open science questions, but maybe we can come back to those a bit later on in this discussion if we like.
Well, thank you very much, Julie. There's a number of questions coming through, and I'm sure we won't have time in the next 15 minutes to cover all of them, but I'll try and extract some of them. And we've got to remember this conference is about deep tech and the impact that Attract projects have had, which are technology focused, but as we've seen, it's not just the technology, it's the social interaction, it's the interaction with the environment as much as everything else, and trying to get this holistic picture. And one of the questions is really about public access to all this information. I've been a proponent of open science and open data for many years now, but is it a reality, a likely reality in Europe, or is it really a myth? Especially as we look at Attract and we hear from John David Marlowe about the bringing up of new companies, and Julie's talked about the problem of companies holding on to information. How does that become publicly available and useful to the wider taxpayers who are paying for it anyway? And so are we as the general public going to be involved in all this movement, or is it going to be in a domain which we don't see? Who's going to, Tony, can I get you to kick off on that one? Tony, you're muted. Tony, you're muted.
Yeah, I'm muted, yes, sorry. Yes, no, I think that's an question. I think there is a general principle that if it's paid by public money, then it should be available to the public who paid for it. But I think it's also reasonable to the people who devised the experiment to get the data have a period of time where they have unique access, that they can do the analysis. And therefore, I think it is a balance. That's that type of data, but there are companies, the big IT companies, who are not publicly funded, who actually generate huge amounts of data, some of which they let us see, But I think it's, as Barbara said, just the tip of the iceberg, that we only see a tiny piece of the data that they've got. And as Tuli and Barbara have said, you know, there's a lot more we could do if we had more data. I think these companies are beginning to realize they have a social dimension to the rest of the countries who actually use their services. But I think there's a long way to go. And I think that we need to keep the pressure up to make sure that they release data that we can reasonably be expected to see and analyze and use usefully.
Well, one of the issues that I'll come to Tuli in a second. One of the issues that has come up is how we train people from the age of 0 to actually take part in this new data-intensive world, and especially to interface with their environment. Tuli, please make your contribution.
Yes, so somehow I think that when thinking about this publicly funded question and sort of when something is publicly funded, so then there is an obligation to be providing benefits for the public as well. So I think that even these big social media companies are publicly funded in a way because their business is data and it's our data, isn't it? So we are contributing to the companies. And in that way, we are funding the companies, if you will. So in that sense, somehow making sure that that information is not only used for business and even manipulation of thoughts, but also for social good somehow and for decision making. I, for example, have been working a lot with urban planners and regional planners, and they would very much benefit from information that big companies have access to and can be making their decisions on, while the societal actors actually don't have this information at their hand when making decisions. So somehow making sure that those kinds of mechanisms are in place. And I think that there is a call for some sort of a system where we would have open data products developed from these, of course, very private, very individual level information, but data products that would be readily available for decision makers. And on the other hand, research environments that would be allowing researchers to access these data in a safe environment without compromising privacy. And that is somehow something that I would really like to see that Europe develops overall. And then for the openness, I think that would somehow help in also advancing open science, because of course one of the challenges is that at the moment we do have access to some of the data resources through individual negotiations, for example, as we have been successful in negotiating data from mobile phone companies. But that's not anymore very open science then, because we can't be providing the data to other readers of the papers, or others can't be accessing the data to check our results. And I think that is worrying from the perspective of open science. So even because of that, we should be striving for these new mechanisms for having access to the data collected by these companies.
Thank you. Barbara.
Yes, I think this is a very important issue. And I think what is needed is to have also communities that are managing the data, because it's not only sufficient to get the data, but it is necessary to have curated data. So we know, especially if they have been processed, we have some information about the data itself. We know about the quality of this data, and we need mechanism for sharing those. So not only the data and possibly tools associated with the data, but also the ability of evaluating how to contribute to the data in a good way, and also improving the quality of the data along the process, and creating community focus on different problems possibly. This is already happening in some of the communities. I'm thinking, for instance, there is Copernicus with emergency mapping services, where maps are available to everybody, but there is behind a very tightly curated processing of the data to gather the information from satellite data, other sensors, and producing the maps. And quality control in this process is very important. And it is true for all the data, because just getting the data is not sufficient. So I think that we should build more sophisticated mechanisms for doing that, not only for a specific service like the one that I was mentioning, but also for sharing data and associated software for processing it in an easier way.
Yeah, thank you. I mean, the Attract project has a strapline of open science for open innovation, creating jobs in Europe. And I just wonder, as we were listening earlier to some of the talks in the introduction, about how we balance this whole thing between open science and open innovation, where you do need some technology or information lead. One of the questions is about the fact that open data is all about old data and not current data. In other words, the researchers have at least an embargo period of at least 6 months or longer, depending on the area, and how we actually overcome that so that actually we start to get confidence that that open science really does lead to open innovation and jobs in Europe. Anybody you want to tackle that one? I think I've stymied you. Let's look at the few. Perhaps Tony, please.
No, I think it's very difficult, but I think that the world is facing. What I think can change things is there are major issues now which are more than just national issues like environment and so on. And I think we've taken a lot of data over the last 50 years in environmental science and in geoscience and so on. And actually now we need to use that data to try and solve the problems that the world is facing. And we have new technologies to help us. We have resources. And I think that in certain areas, I think there is real hope that open science can be open innovation that can lead to solving some of the problems. And in solving the problems, you will create new jobs, new industries, which are carbon neutral and so on. So I'm not entirely pessimistic, but I am a little bit pessimistic about wanting to get all the data from the companies. When you sign up to use Google or Twitter or whatever, or Facebook, the deal is you get all these wonderful services for free in exchange for giving them your data. And that's the deal. And it was always the deal. And maybe you need to renegotiate. Maybe we pay for some of the services and then we have a right to some of the data. So I think in areas like environment and challenges which are global, water and famine and so on, yes, we can do some open innovation and create new jobs, but other areas are a little more complicated.
Thank you, Tuli.
Yeah, thank you very much for this comment. I think that it was to the point, and that's indeed the challenge. Somehow I'm thinking that it doesn't, like, openness doesn't always mean that it has to be cost-free, but it has to be somehow transparent. So somehow we do need to have, of course, mechanisms for funding the data that we want to be having at hand. So it doesn't mean that everything should be available free of charge, but that it would be available with clear principles, transparent processing chains, and so on. So that is what I think we need to be calling for. And that would be important for the openness of science. But it is a challenge that how to generate business out of openness. But I think that at least in Finland, we have seen cases which have been successful, building on open research work and then having spin-offs on top of that, and developing still the open protocols forward, but adding something that the customers are willing to pay for, even if doing things openly. And I think that is possible, even if not easy. But maybe in this big data discussion, one of the things that even if being excited about it, I would like to be sort of bringing us back to the fact that people don't always know, or we can't expect them to be able to manage their own data. For example, these My Data initiatives have been fantastic, but then if we think about vulnerable populations, for example, yes,
thank you.
Okay, so just that make sure that we would make sure that it's not elite that decides on how things are being done and elite data that is being used only.
Thank you. Well, we've come to more or less the end of our session. There are big questions about ethics, for instance, and how we take AI forward. And I think that could be something that the second phase of ATTRACT looks at, and its implications for social sciences and the society at large. Also, too, about what the implications are for jobs. Look, you've got 15 seconds each to give me one strapline that the audience can take home. We'll start with Tony.
Big data, AI, and end of Moore's law. Really a wonderful convergence of technologies which can make dramatic changes. So I'm really positive that we can do great things with that.
Barbara.
I'm also positive, but I think there is a need to study more which are the results of our automatic analysis. So to be able to understand them better, to share them better, so that communities can be built around those.
And Tuli, finally.
Yes, on top of the things that we discussed, I think that somehow I see that deep tech is transforming the way how we do science in the end. And that is, to me, one of the most fascinating things, being a multidisciplinary or transdisciplinary scientist, how difficult it is to be grasping the scientific literature that is vast and growing, but whether we could be having deep tech as a tool for us to be summarizing the current scientific knowledge for human brain. That is what I look forward to.
Well, thank you all very, very much. And look, there have been a number of questions which I've tried to synthesize some of them into one, but I hope you will contribute them to the speakers so we can follow this up afterwards using the Slido links. And thank you very much once again to all three speakers. It's been very stimulating. My strapline is the future is not what it used to be. So get used to it and enjoy. Thank you very much, all of you.
Thanks very much, everybody. Thank you.
Yeah, thank you for our first panelist. I mean, it was our first live panel of the day. So thank you, John. Thank you, Tony. Thank you, Barbara. And thank you, Tuli. Indeed, I mean, we can't really look into technology and innovation in isolation. So we have to take the bigger context.